Hey everyone, this is my third time trying to record this video and it keeps messing up. So fingers crossed this is the last one. We have a situation where a magnet just will not stay stuck on the fridge. I'm sure you've had this experience before. So like this magnet, it's just keeps sliding down. The reason why this happens is because the force of gravity must be bigger than the frictional force that normally holds up the magnet. Now I tell you in this problem that the frictional force here is 0.8 newtons. But if it's a zero point 0.1 kilogram magnet, well, that's a 1 Newton gravitational force. Now, there's more than one way to solve the problem, but basically my question is this. How far will it drop before it's going 1 meter per second? And how far will it drop before it's going 2 meters per second? Remember, the whole time, though, it is pushing against friction. So the last thing I want to know is how much energy does end up getting stored in friction. Remember, as you rub things together, as things collide, as things hit things, that energy gets stored thermally. So let's go ahead and start off by drawing an LOL diagram. L, L, L. So each of these L's, this is when the magnet is not moving. This is the magnet when it's going 1 meters per second. This is the magnet when it's going a total of 2 meters per second. I'll throw LOs here, although I'm not going to have any work done here. I will make my system the magnet, the fridge, because I'm assuming some of this energy is going to get stored in the fridge as well, and the earth, because we want to use energy stored gravitationally. We need the earth in there to make this happen. So let's think about what's going on here. How is this energy being stored? And so at first, well, it's not moving, so it doesn't have any energy stored kinetically. We haven't warmed it up. We haven't slid it against friction, so any energy stored thermally is also zero. But it's higher, right? It is physically in a higher position against the Earth's gravitational field. All of the energy that's currently in this magnet is stored gravitationally. So the way we're going to show that is I'm just going to put a whole bunch of boxes into this gravitational account. In fact, I'm going to do 8 boxes because we got to split them up a bunch. Now here, it's fallen a little bit, right? So it's not as high up on the side of the fridge. So I'm going to take out some of these boxes. But now it's moving. So some of this energy now is stored kinetically. And it's rubbed itself on the side of the fridge. So now some of this energy is stored thermally. Over here, it's fallen even further. So the energy stored gravitationally is even smaller. It's going faster. So energy stored kinetically is bigger. And it's rubbed even more on the side of the fridge. So the energy stored thermally is bigger as well. If I did this right, these add up. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Ooh, I have one too many boxes. 1 second. Let me get rid of it. All right, better. So we end up seeing how all of our energy that was stored gravitationally is now getting split up amongst these other 2 accounts. So let's see if we can use this. So to start off, let's think about what's going on here. All of the energy here stored gravitationally. Here, that energy stored gravitationally will have gone down. The energy stored kinetically has gone up, and the energy stored thermally has gone up. So the amount of energy stored gravitationally, however much that went down, will be add that to the amount of energy stored kinetically and the amount of energy stored thermally, and that should tell us how much energy we had stored gravitationally to start with. And then finally over here, same thing. The energy stored gravitationally plus the energy stored kinetically plus the energy stored thermally should add up to be the same as the energy stored gravitationally in the beginning. So what's important here is each of these times I've drawn EG, it's a different EG. This is the EG in this plot, this is the EG in this plot, this is the EG in this plot. This could be 5 joules, this could be then be 4 joules, and this could be 2 joules, right? We don't know exactly what that is. That's actually our goal to find out. So this is how you set up these problems, and this is how things get split up. Now the next part is the math. Now I'm going to admit this problem gets a little weird. And the reason why it gets weird is because I forgot to tell you what height this magnet starts at. If I told you what height this magnet starts at, this problem actually gets a lot easier. So I'll tell you what. I don't know. You guys have a request? All right. So if you want to try this problem yourself, if you think you could do it, you could go ahead and say that it starts off with a height of 10 meters. That, I think, would be a reasonable place to go about it. Now, no one's fridge is actually 10 meters tall, and I'm going to be honest, I probably would have expected, I think when I do the math, it ends up needing a huge fridge, but it's my fault for posting the problem before I actually work out the answer. So let's assume it's a huge fridge, and it goes 10 meters, and yeah. Now, it is possible, by the way, to not know this or to not use that number. You can put in any height you want. So remember, it's just like some of our old, 7.1 problems. You can call that point whatever you want. If you want to, you can call it 0, you can call it 10, you can call it whatever you darn well please. You just have to make sure that it's the same reference point as down here. So if you guys want to if we can call that 10, I think that's a good place to start. I will admit this is, like I said, it's the third time doing the video. The last 2 times I did it, I started from 0 meters, and I just decided it was too confusing, so we're redoing it. So we'll say it's at a height of 10. You could have picked any number here, including 0, and it would work out just fine. So let's figure out how much energy do we have stored gravitationally to start with. Well, we know that the amount of energy that this magnet has stored gravitationally to start with will be its mass times 10 newtons for every kilogram times the height, which we said was 10 meters. So 10 times 10 times 0.1, that ends up getting 10 joules. So we have 10 joules of energy stored in this magnet initially gravitationally. That will change depending on what height you used. Like I said, initially I chose 0 for this, and so it had 0 energy stored gravitationally. Well, here we're going to get something less than 10, right? The energy stored gravitationally is no longer to be 10 because some of this energy is now stored kinetically. In fact, we can figure out exactly how much. 1/2 mass times velocity squared. So that's 1/2 times 0.1 times 1 meters per second squared. 1/2 times 0.1 kilograms times 1 meter per second squared. So 1 times 0.1 is just 0.1, and half of 0.1 is 0.05. So there's 0.05 joules stored kinetically at this point. It's not a lot of joules. That makes sense. It's not a very big magnet. But that means that of those 10 joules we started with, this much has definitely moved. Now, how much has it changed? So the mass times this 10 newtons per kilogram, but remember the height used to be 10 meters, but it's not 10 meters anymore. Now we've gone down a little bit, and I don't know how much we've gone down. Similarly, on this side, I know that the amount of energy put into thermal account is equal to the force of friction times however far it moves, which is, again, this little h thing. So I'm going to go ahead and expand this out. 0.1 times 10 is just 1 times 10 meters. This is newtons per kilogram. Sorry, 1 newton per kilogram times 10 meters minus h times 0.8 newtons times h. We end up getting here that the 100 newtons per kilogram times 10, that is our 10 joules, minus 1 times negative h. So h number of joules. So h newtons per kilogram plus 0.5 joules plus 0.8 newtons. Where am I missing? Oh, we already used the kilogram, sorry. The kilograms got canceled out when I multiplied by mass. 10 joules minus h newtons plus 0.5 joules plus 0.8 newtons times h. Combining like terms. So this is 0.8 newtons times h. This is just h newtons. So what's h minus 0.8h? So these two add together to be 0.2h. So 10 joules minus 0.2 times h number of newtons plus 0.05 joules will all add up to have 10 joules of energy. We can see right here then that these two must have an equal opposite value, right? The 0.2 times h newtons plus 0.05 joules must annihilate each other. So let's go ahead and calculate that out. We end up getting 0.05 divided by 0.2, which ends up being 25 centimeters. Oh, sorry, 0.25 meters. So, like that's a tricky problem. Look, we see how much the energy stored gravitationally had to go down. It had to go down by some number of newtons. Well, the energy stored thermally had to go up by 0.8 times h, whatever that is. The energy stored kinetically went up by some amount. The only way to make that happen is it has to have dropped 1/4 of a meter. That's the only way to make this all work out. We can do the same exact math over here. The only difference ends up being, in fact, I'm just going to skip over to the end. We know that the total energy of 10 joules has to now be equal to this negative 0.2 times h newtons, plus it's just no longer 0.05 joules. Now we know it's 1/2 times 0.1 kilograms. Now it's going 2 meters per second. So 2 meters per second squared. So we have to add to this guy right here. 2 becomes 4, 2.2. We end up getting 0.22 joules. So again, and sorry, I forgot the 10 joules here. So again, we see that these two must be equal to each other, equal and opposite to each other. And the only way to make them equal and opposite to each other then is that our h is equal to 1 meter. So we see here, it will have dropped 1/4 of a meter to go from here to here, and a whole meter to go from here to here. I think this is probably a little bit more complicated than I'll just tell you right now. I don't like giving you guys problems with this thing going on, where we have this change in height. I think if we were really to do this problem properly, if I were to release this problem, with enough lead time that I actually test it out first, I probably would have chosen a different height. I might have made the magnet go uphill or something like that to make the math work out a little bit easier. But the main thing I really want you to see here is look how the energy gets split up in our LOL diagram, and then look how we account for that mathematically. Solving for h here is absolutely tricky, but that's an exercise in algebra more than it is in physics. So the number one thing if I want you to pay attention for me is this. If you can look at this situation and get to there, then this part right here with the algebra is little secondary. Um, I don't think I've given you any problems this complex for evidence assignments, and I don't think I will. But you asked for a complex one, so here's what I'm giving you. Forgive the ugly algebra here. This would have been something I would have liked to have laid out a lot nicer, especially considering this is the third time I've tried to make this video. Please do let me. Oh, we didn't even answer the final question. Gosh. So when it's all said and done, we want to know how much energy did end up getting stored thermally. Well, we know that the amount of energy you end up getting stored thermally is just equal to the amount of work we done against friction. So that'll be the force of friction times however far it has moved. Well, it's gone 1 meter. So 0.8 newtons times 1 meter, we end up getting 8 joules. We're going to end up getting 8 joules of work just into the thermal account, which may not be much, but it'll warm up the magnet a tiny bit, right? All right, everyone. I'm hoping that didn't make things worse. If nothing else, you can see how you see I go through the LOL diagrams, how I split it apart, how I use it algebraically, even if all the algebra sort of got cut off and jumbled just because I physically didn't place it very nice. And also, I'm real sorry. I should have given you that 10 meters to start with. You don't need it, but I just don't think it's appropriate for our level for me to expect you to deal with that yourself. All right, everyone. Do let me know if you have any questions. And yeah, have a nice day.